Assalamu alaikum. Hello, everyone. Before we continue from where we left off, I would like to mention something very briefly. So you remember when I talked about the initialization of the centers? Okay, the first method is the random initialization. The second one used in k-means plus plus is actually you choose the first center to be one of the points. Okay, maybe that's the thing I didn't clarify. So every point has equal probability to be chosen. So you uniformly sample the first center. Okay, once the first center is defined, then the second center, and the probability of sampling, it will be another point, but the probability of sampling will not be uniform, will not be equal anymore. So you're not uniformly sampling. So the ones that are further away from the first center will have higher probability to be chosen. Okay, the probability of choosing a point is proportional to the square of the distance between that point and the first center. You pick the second one, the third one, the same thing. Okay, the probability of choosing the third center has to be the one that's very farther away from the max of these distances will have higher probability to be chosen. Okay, these details are not there, but since I mentioned them, because last time I said like we choose the first center and then the second center, the distance, the probability of choosing that is proportional to the square of the distance, but I didn't maybe mention that these centers are actually points in the data itself. Okay, and then when we start updating, then they may become something that's not one of our data points because we're taking the mean at every time. But at least that's the starting point. Okay, since I mentioned, I just wanted to clarify it. Okay, so we stopped here last time. So you remember we talked about like choosing K. Like defining K is very like choosing the number of clusters or K is very crucial step. Okay, so that's why actually what we do, we choose different choices for K, and then we cluster based on that, and then using some metrics, we make a decision about which K is the most reasonable one to choose. Okay, what is the most reasonable choice for the number of clusters? There are metrics. Okay, to measure that. You remember, like for example, for classification, for regression and classification, we used to rely. For example, for regression, we used to rely on the mean square error to decide which algorithm and which choice of the hyperparameters is the best. Okay, the one that achieves the minimum mean square error is the best model. Okay, and the best choice for the hyperparameters. Okay. So for the classification, we rely on the accuracy as well as the confusion matrix, right? So here, for clustering, so to measure or validate our choice for the number of clusters, there are actually two categories, okay, of metrics. There's what we call external and internal metrics. For the external metrics, they require the ground truth. So they need to know the actual label, but that is somehow contradicting the assumption we have in clustering that we have no labels, right? So think of this like as a method, is a valid metric you can use when you actually are casting a classification problem as a clustering problem, because always you can actually cast a classification problem as a clustering problem. So you ignore the labels and you try to cluster points, and then you see how good you're doing in that. Or maybe, for example, if you have like some synthetic data that you can use to train a clustering algorithm, and then you want to run it later on, maybe on on a real data that is similar to what you have to what you have had labels for. Okay. So it's also, this works for any shape of clusters. Okay. We will come to this. We will explain this later on because we will have two examples later on that will explain what do we mean by for any shape. Okay. I'm coming to that later on. So the internal ones, they do not have access to the ground truth. So they don't know the actual label. And that seems to be more realistic measurements for metrics for the for measuring the quality of the clustering, because in most of the clustering problems, we don't have access to the label. Okay. So they are based on some like comparisons between between points in the same cluster and points outside in different clusters. So like how much, for example, one of them, as we'll see later, it looks like how much the data points within a cluster, or the proportion of the scatter of the points within a cluster compared to the scatter between clusters. We will look at that later on. So these work well if we have convex shape for the clusters. If the clusters are of convex shape, and I will explain this later on, as I said. So, but for now, you need to know like this can work. The external ones, they can work for any shape, and these they work only. They are reliable. You can rely on their outcome when the shape is convex. When the shape is not convex, they may not. They could be misleading, and I will talk about this. I will come to this later on. I will explain what do we mean by convex shape. Okay, so here are four of them. Okay, so four metrics. Okay, the adjusted RAND index, ARI, normalized mutual information, NMI, Salute index, SI, and Davis-Baldwin index, DBI. These are four metrics. The first two are external. The second two are internal. The first one goes from -1 to 1. This goes from 0 to 1. This is from -1 to 1. And this goes from 0 to infinity. So for the first three, higher value is better. So the choice of K, or the number of clusters that maximizes the value of these three, okay, is the best choice for K. The one that minimizes this for the last one, the K, the choice for the number of clusters that minimizes the DBI is the best choice you should go with. So as I said, the first two are external. Okay, they need access to the ground truth or the actual label. The last two, they are internal. Okay, they learn from the data itself. So if you look, for example, here is the meaning. Okay, so for the first one, it's the proportion of corrected clustered points. So actually, this translates to the accuracy in the context of classification, right? So this is the accuracy. So higher accuracy is better, of course. Okay. So this one, like it's rooted in information theory. It's about like how much information is captured by every choice of K. These, as I said, they are from the data. They do not use the actual label. Okay, for example, let's look at this one here. It's the ratio of the within cluster scatter to the between cluster separation. So now think why lower is better? Because actually, if the points within a cluster are very scattered compared to the separation between clusters, then the value is high. Then that's because it's the ratio of that, right? It's the ratio of the within cluster scatter or to the between cluster separation. So if the points are more scattered, the ones that you include in one cluster, they are scattered, then that will be high. So you want like the points within cluster to be less scattered. Then if they are less scattered, then the proportion is lower, and the choice of K is better. Okay, that's at very high level. For this course, what you need to know is like these are the four metrics, and these are the ranges. And for the first three, higher K is better. For this last one, lower K is better. Okay, these are internal ones. They do not assume or use the label or the ground truth. These they assume like they use actually the ground truth or the actual label. So if you have the actual label, then you rely on this, and this will give you more reliable return compared to these two. Okay, let's look at this example here. We're gonna load the data of this file. Okay. We have an error here. What was the error? Clustering to why that is not there. That's so weird. Uh, Let me check. No such file or directory. No, it's this, right? Okay, so we loaded the data. Okay, so here we have two features and we have the actual label here. Okay, and then here. Okay, so what are we doing here? Okay, so we're gonna choose K to go from 2 to 15, 2, 3, 4. So we have 13 choices for the total number of clusters. Okay, so we are dropping the label, and then we are creating empty arrays for each one of these metrics, because we're gonna empty arrays, the length of the len or the length of each array is equal to the number of choices for K, because for every choice for K we're gonna compute one value for each of these metrics, and then we're gonna plot in the x-axis the choice for K, and the y-axis what was the value for that metric. Okay, so then we are iterating over these different choices for the number of clusters, and we cluster based on that. So in the first iteration, we assume like the number of clusters is equal to 2. So then we will perform k-means, assuming like there are 2 clusters. Then we will compute each one of these metrics. Okay, as you can see, the first two, the SI and DBI, they do not require the label. That's why we pass the first input is the data, the second input is the labels returned from k-means. Okay, because when we do clustering, we return labels here. Okay, so the first input is the data, the second input is the labels returned by k-means. That's for the first two, because they are internal methods. They rely on data. They do not assume, or they do not have access to the actual label. For the second two, okay, the first input is the actual label, and the second input is the returned label from k-means. Okay, and then, yeah, then we compute both of them. Actually, in fact, this one is nothing but the accuracy. So it's going to compare how many times they are equal and divided by how many, the total number of data samples. Okay, so then we are gonna plot each one of them. Let's look at them here. Okay, by looking at this, and by the way, this example, this is actually this example here. Okay, did we plot it here again? Let me first, yeah, it's this. Okay, as you can see, this can be approximated by each one of these clusters can be approximated by a circle. And the circle is of convex shape, because in general, a convex shape is like a shape where if you pick any 2 points, okay, if you connect these 2 points with a line, all the points in the line that connects these two points belongs to the same shape, okay? So belongs to the data set, okay? So if I put this inside the circle, then inside that circle, any 2 points, if I connect them with a line, any point in that line that connects any 2 points still belong to the circle, okay? So this is convex shape. So I will assume all of the metrics will be able to identify that K is equal to 3. It's actually, every one of them is almost convex shape, and it's very simple example here. There is like a clear like separation and distance between different clusters. So I will assume, before even looking at the metrics, I will assume the metrics, or both metrics, the internal as well as external, will somehow have agreement on K. And in fact, and they will all choose like, okay, let's look at it together, okay? So let's start with the blue one. The blue one, remember, for the blue one, it represents the DBI. So lower value for that means better K. And the lowest value is at K equal to 3. Okay, so this one, if we are looking at this metric is telling us that K equal to 3 is the best choice. Okay, there are three clusters here. Okay, now let's look at the other three methods. For the other three methods, the K that maximizes the value of that metric is the best K to choose. And for all of them, for the three of them, they are all reach their maximum at K equal to 3. Okay, so this, by the way, these two, the SI and DBI are the internal ones. Okay, and these two are the external ones, the ARI and NMI. Okay, but there's an agreement here. All the internal as well as the external metrics are telling us that when K is equal to 3, okay, k equal to 3 is the best choice to choose, okay? And here we just like plot them, okay? So we plot a scatter plot for A versus B, and we pass the labels. Sorry, we color the points based on their labels, and this is what we get, okay? These are the three clusters, cluster 0, cluster 1, and cluster 2, okay? So now let's look at another example, okay? Okay, let me, and so this is another example. We're doing the same here, okay? We have loaded the data, and we are doing the same, okay? So let's run this code and look at the outcomes. Here, now seems to be like there's no agreement, okay, between the different methods. So if you look at the blue one, it's telling us that k equal to 6 is the best choice, okay, according to DBI, which is an internal method, doesn't rely on the actual label. It just like uses the data. So it's telling us that like because the choice of k that minimizes this is the best choice for k. So the minimum value for this metric is at k equal to 6. So this one is telling us like k equal to 6 is the best choice. Maybe for the SI, almost same, maybe between 6 and 7. Okay, so these are the two internal methods. Now let's look at the external methods. Okay, the ARI is telling us like that 4 is the best choice. When k is equal to 4, we achieve the highest value for the ARI. Okay, for the NMI, the highest value is at k equal to 5. Okay, let's look at this data here. Let's plot the uh, feature A versus B. As you can see here, 4 seems to be the most reasonable choice. So this actually, the data represents 2 eyes, nose, and a mouth. So there are 4 clusters. So it seems that ARI is doing the best job here in finding the best K. The ones that rely only on, the ones that do not have access to the ground truth, the internal ones are actually telling us that there are 6, okay? And the NMI is saying that there are 5, but the most reasonable choice here is 4. And as you can see, this shape here, this one here, is non-convex, because if I take a point here and a point here, and I connect these 2 points with a line, most of the points in this line, they are not belong to the cluster, to the shape. So this is non-convex. And when we had one non-convex shape, the internal ones, the decision of the internal ones was not so reliable. Okay, so maybe let's look at the what. Okay, so let's follow what this one is telling us. It says like there are 6 clusters. Let's rerun the k means, and we specify that the number of clusters is equal to 6. Okay, let's look at these 6. Okay, this one has been divided into 3 clusters. Okay, so 1, 2, 3, 4, 5, 6. Okay, so this one is not considered as one cluster. Okay, so that's the idea. Okay, at very high level. And in fact, it's divided here now. If you look at this closer to like convex shape, any 2 points here, the line between them will be belong to the shape. Maybe here, yeah. Here, not really, because if I take point here and point here, they are the line connecting them. Many points in that line will not be belong to the shape. This is like that one, okay? But yeah, anyways, that's the idea. So here, yeah, the internal ones were not so accurate, okay? But not too bad as well, right? Okay, so maybe let's stop here for today. So I think next lecture, inshallah, will be the last lecture. We're gonna go very briefly through 2 case studies. And with that, we finish, inshallah, this series of lectures. Thanks for watching, and see you next time. Assalamu alaikum.